In this video, we cover the solutions to Test 3 of the Fall 2013 AP Physics course. The area under an acceleration time graph gives the change in velocity. One way that you can see that it has to be at least velocity is that if you have acceleration up there, which is in meters per second squared, and you had some time here in seconds, and this thing maybe went like that, this area here has the units of a meter per second squared times a second, which would be a meter per second. So it has the units of a velocity, and in fact this area is delta V. It depends on a start and a stop, so it has a change. Any area will always have it be a change. The slope of the tangent line on a position time graph, by definition, is the instantaneous velocity. If you leave off the word instantaneous, that's fine, because if we don't say instantaneous, we mean instantaneous. If we don't mean instantaneous, we have to, like for instance, want to do the average velocity, we have to say average. But if we don't say anything, it's understood that it's instantaneous. The slope of the chord of a velocity time graph gives us the average acceleration. So that's the answer to number 3. Average acceleration. And what you're looking there's velocity, there's time, and you have some curve, and the line from here to there has a slope, delta V over delta T, and that's the definition of average acceleration. The area under a velocity time graph gives the displacement, which is the change in position. The slope of the chord on a position time graph gives the average velocity. The slope of the tangent line on a velocity time graph gives the instantaneous acceleration. So problems 1 through 6 were simply checking out definitions and your understanding of motion curves. We now go to question number 7. In question number 7, it says to perform any calculations required and to write your answer and box it. After performing the experiment, you find your data plotted on a position time graph gives a straight line. Okay, so we have xt, and it's got a slope of 3.43 and a y offset of 1.45. So this is 1.45, which is the position x at 0, the initial position, and then it plots a straight line, and then the slope is 3.43 meters per second. This is an example of a constant velocity graph. What's the object's velocity at 3 seconds? The same as it is at any other time, since it's constant velocity. 3.43 meters per second. At least that's our best guess based on the fit. What is the object's displacement? Now, to find displacement from 1 second to 3 seconds means that you need to find the change in the object's position. So we're looking at delta x is equal to x at 3 seconds minus x at 1 second. Now, if you plug that in, what you're looking at is x a times 3 plus b minus a times 1 plus b. So delta x is a times 3 minus 1. So what is it? Well, A is V. So what you're really saying is you're looking at V times delta T. So 3.43 meters per second times 2 seconds. So delta X is equal to 6.86 meters if my calculations are correct without a calculator. And of course this makes total sense. Distance is equal to rate times time. People often say it's dirt. What is the object's acceleration? It's a constant velocity, so acceleration is 0 meters per second squared. It's a constant velocity problem. It is not accelerating. What's really being checked here is if you really learned those motion graphs and have really gotten what you needed to out of all the Logger Pro activities we've done fitting various types of cart. This is an example of the constant velocity carts that two of your things that you had, I think it was number 1 and number 2, in the activity on the moving carts. Moving to the next one, in problem number 8. Now in problem number 8, we're told that we have an acceleration time graph. It's a different type of graph. Acceleration versus time. It starts here at 4 meters per second squared, and it goes up at a rate of 2. So we're later going to be asked about 1 and 3 seconds, I believe. And if I look at this, it goes up by a rate of 2. So in one of the later parts, part C, I'm going to need to realize it goes up by 2. This is going to become 6. And when it goes up 3 times 2, it's going to have taken this up to 10. Alright, so I'll need that later on. What type of motion best describes this? Well, it's not a constant acceleration. That would be a horizontal line. It's not a stationary object. In fact, what this is a variable acceleration graph. What's the object's acceleration at t equal 3? Well, 2 meters per second cubed for the slope times 3 seconds plus 4 meters per second squared gives you 10 meters per second squared. And that's the point that I just graphed right here. What's the change in the object's velocity? Now that's a little bit more of a trickier type of problem, because what you're basically do to find the change in velocity is you need to find, oops, now let me change my pen color. You basically need to find that area. Now you can do that a couple ways. You can come across here and find this triangle, and then find this rectangle, and that will get you what you need. So let's do that. Let me change my pen color back. Delta V is the area under an AT graph. So delta V is the rectangle. The rectangle's height is 6 meters per second squared, and its width is 2 seconds, plus a triangle who is 1/2. It has a height of 4 meters per second squared and a width of 2 seconds. I put that into there, and I get 16 meters per second. What is the object's acceleration? or average acceleration from 1 second to t equal 3 seconds. Well, A average by definition is the change in velocity over the change in time. So that's equal to 16 meters per second over 2 seconds, which is 8 meters per second squared. Now, because that line was a straight line, alternatively, since we have a straight line, A average could also be found by taking the acceleration at 3 plus acceleration at 1 and dividing by 2. So if you did that, it was 10 meters per second squared plus 6 meters per second squared over 2. And when you plug that in, you get that A average is 8 meters per second squared. All right. I believe that solves that particular problem, and we'll see you on the later video for the rest of this exam.